done in 2016 as part of the high-scale campaign. This project was a collaboration with Aerodyne Research, and so I'd like to thank various members of Aerodyne, in particular Harold Stark, and then I'd also like to thank Jim Smith, who was one of the organizers of the ground-based measurements during the high-scale campaign. I'd also like to acknowledge funding for this work from the Department of Energy, and ARUB has been supported by an NSF Graduate Research Fellowship. So why are we interested in nitrogen chemistry? So if we think about nitrogen, we could think about either N2 or reactive nitrogen. Reactive nitrogen will be the forms that are chemically, photolytically, labile. So pretty much any type of nitrogen other than N2. If we think about how do we convert N2 into these types of nitrogen that can be utilized, there's natural processes, and that's pretty much just limited to lightning and biological nitrogen fixation, BNF. We also have denitrification, which is the process of turning the reactive nitrogen back into N2. And then there's also anthropogenic induced pathways. So those include combustion, fertilizer, and agricultural biological nitrogen fixation, or BNF. As a result of these anthropogenic activities, we've drastically increased the amount of reactive nitrogen that's being introduced into the Earth system. So in this plot on the upper right, on the x-axis, we have year going from 1850 to present day-ish, and then reactive nitrogen creation in teragrams of nitrogen per year on the y. This reddish color line is the total nitrogen creation, and you can see that it's just skyrocketing after about 1950 or so. This is due to a combination of energy production as well as agriculture. So the Haber-Bosch process, creating ammonia for fertilizers, has been a large driver. You can see that in the green line. And while this has allowed us to do things like feed a growing world population and enable industry and all of that, there's been some unintended consequences of this massive input of nitrogen into the system. And that's realized in a few different ways. But first, what we need to understand is that this picture here is just how we create reactive nitrogen. So how do we turn it from N2 into forms that can be utilized? Once it's in those forms, the nitrogen will cycle throughout all the different spheres. So the atmosphere, the biosphere, etc. So you can see I've now added biomass burning onto this slide because biomass burning does not create reactive nitrogen, but it does cycle it between different forms. And so this input of reactive nitrogen will obviously impact the nitrogen cycle, and through feedbacks, it alters the carbon and the phosphorus cycles. And so you can imagine that there's numerous implications for climate and air quality. So just narrowing down from this big picture view into kind of the atmosphere and biosphere, which is what I'm most interested in, we can start thinking about some of the ways in which nitrogen cycles and what that means for our understanding of atmospheric chemistry. So many of you in this room are probably very familiar with the formation of tropospheric ozone through the cycling of NOx. We also have the creation of aerosols, inorganic aerosols, ammonium nitrate, ammonium sulfate. These lead to degraded air quality. They alter radiative forcing. We also have increased fluxes of N2O, nitrous oxide, a greenhouse gas that leads to stratospheric ozone depletion. And then we also have things like ammonia and nitric acid that deposit, alter the carbon balance of different ecosystems through that interplay between the nitrogen and carbon cycles, and can also lead to things like eutrophication. And so although the increase of reactive nitrogen creation has done numerous benefits for society, such as food production, it's also led to these detrimental outcomes. One thing that you might notice when looking at these, though, is that all of the forms of nitrogen in this picture are inorganic nitrogen. So ammonia, ammonium, nitrate, NOx, N2O. But when we go out and actually measure the composition of reactive nitrogen, we find that the organic nitrogen is both ubiquitous and abundant. So this is a compilation of various measurements of the nitrogen speciation in rainwater. The pie charts are labeled by or sized by the amount of nitrogen. And you can see that the black here in all of these pie charts is that organic nitrogen fraction. So while we understand the chemistry of the inorganic nitrogen fairly well, mostly because it's only a select few species, our understanding of the organic nitrogen and what that means for the atmosphere and the biosphere is not as well developed. This is partly because the organic nitrogen fraction is more chemically complex and it's labile. It alters its chemical composition. Its amount changes with space and time, and there's just lots of different molecules. So here are just a few examples of some of the types of molecules that might be there. These are small molecules. We also see quite large ones with nitrogen. So it's really been a challenging process to start looking at this composition and understanding what are the types of organic nitrogen compounds that are important for our understanding of the atmosphere. So some classes of organic nitrogen are fairly well understood. So if we go back to this view of tropospheric ozone formation, many people, myself included, have thought a lot about the chemistry of peroxynitrates and the chemistry of organic nitrates, with particular emphasis on how this impacts ozone production, NOx lifetime, and transport of precursors. So although there's undoubtedly many important and interesting research questions left on those types of compounds, we, for the most part, still understand their basic sources and sinks to a fair approximation. However, there are many types of organic nitrogen that are more poorly understood. An example that has received a lot of attention recently are amines and other organic reduced nitrogen compounds. And this has been in part due to the ability of amines and other organic reduced nitrogen compounds to stabilize freshly nucleated and growing atmospheric clusters. So their importance for new particle formation and growth. The cloud measurements have shown that just PPT levels of amines can enhance nucleation even when compared to concentrations of ammonia orders of magnitude greater. So here I'm showing here is just an example of a new particle formation event from the field site that I'll be discussing. So stepping back for a second, the measurements from cloud and then associated measurements from other groups looking at how organic reduced nitrogen impacts new particle formation and growth have really looked at a lot of different compounds. So people have been interested in alkyl amines. They've been interested in amines that look like these compounds because of their proposed use for carbon capture and storage. There's been interest in diamines, and then things like amino acids and urea. And while people have generally found that these sorts of compounds will influence new particle formation and growth, albeit to varying extents, the major problem is that we don't really know that much about their chemistry. We don't know their sources or their sinks, or in some cases, even if they exist in the atmosphere or not. So we'll just step through an example. So we'll take an alkylamine. as an example. So in general, we have a fairly good understanding of what the sources of this sort of compound is. We know there are sources from agriculture, marine sources, some combustion, biomass burning, but in general, we don't really know that much about the magnitudes. Our understanding is really drawn from just a handful of studies. We know that the amines will react once they're in the atmosphere. They can react with OH, they can react with nitrate, they can react with ozone, but it's too slow to be of importance. They do not typically undergo photolysis, and they can also be lost to aerosol formation and uptake, but we don't have very good constraints on kind of the relative strength of that term. The sorts of compounds that alkylamines will form in the atmosphere include amides, that compound shown in blue, imines, that compound shown in yellow, and then some the compounds formed in purple and red there that have NO or NO2 added. I won't really be talking about those too much because they're not prevalent in a rural environment. We can also think about how these compounds are removed from the atmosphere, and in general, we don't know that much about them. So this is for a compound that people have been looking at, that there are multiple lab studies on and investigations, ambient measurements. However, if we take all of those different compounds that people have been looking at for new particle formation and growth, we pretty much have to put question marks by all of these different processes. Because as I said, many of these never even measured in the atmosphere before to know if they exist. And so part of what my group is interested in is starting to fill in some of these question marks here. So to do that, we participated in the 2016 Holistic Interactions of Shallow Clouds, Aerosols, and Land Ecosystems campaign. So this was in Lamont, Oklahoma. The pin on the Google map there, and to the right is a picture of the site. So it's a predominantly agricultural area that is mostly crops. So there is not that much animal husbandry in the immediate vicinity. The analytical technique that we used to investigate this was protonated ethanol cluster chemical ionization mass spectrometry, or EthanolCIMS. So we are using the TOFWERK Aerodyne version with the low pressure IMR. And the way that ethanol works as a reagent ion is through two different channels. We can have both a ligand switching and a proton transfer. Ethanol has a higher proton affinity than, say, water. And so you end up being more selective for things that have a higher proton affinity, such as amines, imines, things that are bases, and thus might influence new particle formation and growth. What's important here is that we are using a TOF MS on this, specifically a long TOF, so resolving power of around 9,000. This ends up being important for peak fitting some nitrogen compounds that are of lower abundance. It is also important in that both amines and amides, where amides are an oxidation products of amines, are isobaric. And so quad MS measurements provide some interesting insights into the chemistry of organic nitrogen, but are really measuring the sum of both the amine and the amide. And so here you can see that we can separate out those two species. So I'm going to tell you a few different stories today about what we're learning from these measurements. So the first story that I have to tell you is very short. It is that we did not see any alkyl diamines. They weren't there. It could have been the time of year, but they weren't there. The next thing I'm going to discuss are some measurements of some small alkylamines. We'll first talk about what we think some of their sources are, and then look into their chemical transformation pathways. And then I'm going to conclude by discussing the chemistry of an interesting molecule that we observed. We think this might be the first ambient measurement of it in the gas phase, urea. Okay. So we'll start off by looking at the small alkylamines and talking about their sources. So just to give you an overview of the campaign. So while we were there for several weeks, everything kind of only came together for 1 week, as many people who do field measurements might be very familiar with. But here you see a time series of ammonia. So ammonia is in the black. The yellow background is the shortwave radiation. So you can see when it is day. These are 1 minute average measurements we have here. Then I'm going to go ahead and add in the C1 amine and the C3 amine. During this time period, we did not have measurements of C2 amines because our calibration system was leaking and introducing a lot of C2 amine into the system. While that in some ways is unfortunate because we weren't able to measure the C2 amine, it does give us some nice insights into constraining any potential interferences that I'll be talking about in the future. But so I'll just be focusing on the C1 and the C3 amines here. So their concentrations are on the right axis here. So as is kind of typical for what we expect, ammonia is present at much higher concentrations than the amines. So we're looking at about a ppb or 2 of ammonia compared to single digit to 10 ppt for the amines. Once again, these are all the 1 minute measurements, and you can see that we're capturing actual atmospheric variation here. The site is located in this agricultural region, as I said earlier, and it's fairly homogeneous around the sources are all very similar, as you can see from this windrose plot of the C1 amine. It's not really enhanced in any one direction. So one thing that you might notice in just looking at this time series is that there's obviously day-to-day variability, but there is also a reproducible pattern. If we just look at the average diurnal profile for these different species, which is now shown in the upper right. Once again, ammonia is on the left, amines are on the right. You can see that everything, these 3 species are characterized by this morning increase and decay over the course of the day. So let's think about this morning enhancement a little bit more to see if it provides us any insight into the sources. So here I've just zoomed in on one small section of the measurements. So what I'm going to do to investigate this morning enhancement is I'm going to take the average from 5 to 7 a.m., take that average concentration, and then for each minute between 7 a.m. and 9 a.m., I'm going to take the difference between that 1 minute and that average value. When I do that, I can make this plot here where we have the morning change in the amines on the y-axis and the morning change in ammonia on the x-axis. The C1 amine is shown in green and the C3 amine is shown in blue. So what this plot is telling you is that the amount that the amines and the ammonia increase every morning is correlated between the amines and the ammonia. And we can calculate the slope for that. And this gives us insight into whatever the source is, how much amine is being emitted relative to ammonia. So if we compare this to kind of known estimates, the global emissions estimate of the sum of methylamines to ammonia is 0.6 plus or minus 0.4%. If we just look at agriculture, it's 0.7%. And here we can calculate that same number just by, or we can approximate that same number. This is not truly an emissions measurement that we're doing here, but it's indicative of what the emissions are. So we see here we get 1.6%. And so I would say that overall, given that this is not actually an emissions measurement that we're doing, we're fairly consistent with kind of the global estimate. However, one thing to note is that in the inventory, it implies the inventory has the most of this emission from agriculture coming from C3 amines. In contrast, what we see here is that the C1 amine in that green is much more abundant than the C3 amine in the blue. So the C1 amine has a larger slope. It's also worth noting that the inventory has agriculture being animal husbandry. So the global inventories aren't actually accounting for amine emissions from things like crops or soils, which is what we're seeing here. So even though we're in rough agreement with it, it's indicating that there's these previously unaccounted for sources. Okay, so let's think about where this morning enhancement might be coming from. So in particular for ammonia, this has been observed many times in ambient measurements and has typically been attributed to automobile emissions, residual layer mixing, gas particle partitioning, plant and soil emissions, or dew evaporation. So we can rule out automobile emissions at this site, just given the location. We can also rule out residual layer mixing, because from that previous plot that I showed you, we know that the source is highly correlated between the amines and the ammonia. Since amines have such a short atmospheric lifetime, we don't expect any significant concentrations in the residual layer. We can look at gas particle partitioning. So here I have ammonia in black, and then ammonium from an ACSM that was at the site. The ammonium's plotted in orange there. You can see that ammonium is pretty much flat over the course of the day. So there's no significant partitioning for ammonia, and we anticipate that it's the same for the amines, given the tight correlation between ammonia and amines. So we're going to rule out that as well. So moving on to plant and soil emissions now. So we know a lot about ammonia emissions from plants and soil, and we know that it is a very complex process. And so it's going to depend on the water content of the soil and the ammonium content of the soil and all those things. And then on top of that, the pH of the soil, I meant to say that one. On top of that, the flux is going to be bidirectional in nature. So that means that if the air concentration is low, we'll have emissions of ammonia. And if it's above some compensation point, it's going to actually be a flux towards the soil or the leaves. So this figure on the left just shows an example of a bidirectional resistance model for an ammonia flux. So you can see there is a compensation point for the stomata of the leaf, for the canopy itself, and then for the soil as well. With the measurements that we had during high scale, we didn't have measurements of soil pH or soil ammonium or anything like that. And so it's difficult to estimate what soil emissions might be. But there are numerous models that have tried to parameterize this process. And this figure on the right here is a model of the ammonia surface flux using one of these state-of-the-art models. And you can see pretty much all of Oklahoma is blue, which means ammonia was being emitted from the soil into the atmosphere. And so this was the same year that we were there, but slightly earlier. But I think it's probably safe to say that there is still subsurface flux going on. There's been significantly less work done on amine emissions. There's a group from Finland who measured some amine emissions from soil in the boreal forest. And then there's been some measurements of amine emissions from plants. So we do know that these can happen, but there's nothing like these ammonia models. So I would say it's likely that plant and soil emissions may be playing a role in driving this variability that we're observing in these compounds, but without further measurements, it's kind of hard to put any estimates on that. The last thing I want to look at is dew evaporation. So dew as a source of ammonia has been hypothesized, and there's been indirect evidence for it for quite a while. And then more recently, Jen Murphy's group, in collaboration with Jeff Collette's group at CSU, did some really nice both combined lab and ambient measurements looking at dew as a source of ammonia. So they did some synthetic dew samples in the lab as proof of concept, and then they made measurements in Colorado. So here we have ammonia on the y-axis of both of these, and then local time on the bottom. On mornings with dew, you see that ammonia peaks and then decreases a little. Mornings without dew, there's this enhancement is not observed. So we don't have measurements of if dew formed or not, but what we can do is we can calculate the dew point depression. So what this is the ambient temperature minus the temperature at which dew forms. And so that means the closer you get to the zero, the more likely you are to have dew, essentially. And so if we plot the maximum that we observed in the ammonia or the amines as a function of the minimum dew point observed the night before, we see this very nice relationship for both ammonia as well as the C1 and the C3 amines. So the closer the ambient temperature got to the dew point, the higher the concentration of ammonia or the amine that we saw the next day. And so we're starting to do, so we think that dew evaporation might be a source of these compounds, one that previously has not been considered for amines. And we're starting to do some lab work looking at this. And so this is being done by an undergraduate in the group, Mackenzie Larson, whose picture is shown there. Okay, so let's move on to talking some about the loss process of these alkylamines. So this is just a schematic of the kind of known alkylamine chemistry. The things I want to point out here is that we're going to be considering oxidation by OH because it's going to be dominant for these small amines, and it can proceed either via abstraction of a hydrogen from the nitrogen or from one of the methyl groups. The products that we expect to see in this sort of environment are the imine, shown here. So this is a molecule that has a double bond between the carbon and the nitrogen, or an amide, shown here. We don't expect to see the nitrosamines or the nitramines because of low concentrations of NO and NO2 at the site. So these are some of the first measurements of amines in the atmosphere. And we can see that they exhibit a diurnal profile consistent with something that would be produced during the day from photooxidation. However, if we also put the amide on that, we can see that it has a very different diurnal profile. So here I have plotted the C2 amide. If we're thinking only about methylamine, we would only expect to see the C1 amide. However, the C1 amide is isobaric with the C2 amine. And because we were adding a lot of dimethylamine unintentionally into our inlet during this time period, we couldn't actually measure the C1 amide. So since both of these compounds are expected to be first generation products of amine oxidation by OH, we also think that they probably have similar loss rates. So the imine loss rate has not been previously measured. It's a very difficult molecule to work with, but it's estimated to be, from some theory work, to be about the same as the amide. So if these were to generally have the same source, they have about the same lifetime, I would have expected their diurnal profiles to look much more similar. And so what this is saying to me is that the imines either have some different sources or some other loss processes when compared to the amides. So we can do, well, let me step back a moment. The first thing that this told me is, do I have a measurement interference that could potentially be generating an imine in my setup somehow? So this is where the fact that we were accidentally adding large amounts of different amines into our system came to our advantage. And even when we added twice as much methylamine as what was in the ambient air, we didn't see any noticeable change in the C1 amine concentration. We also didn't see any evidence for secondary chemistry in the IMR that might have influenced any of these results. So I don't think that this unusual profile of the imines, or this unexpected profile of the imines, is due to a measurement interference. So let's do some pretty simplified modeling to think about what might be causing this profile for the imines. So in purple, what I have here is the measured, so this is just that diurnally averaged imine profile in the purple, and then the red, the black, and the blue are all different model results. And so for this very simplified model, I can strain what the amine, the amine concentration is, and I constrain OH. And then I let the imine be formed. In these three simulations here, I have the main loss process of imine being aerosol uptake, reactive aerosol uptake. You can see with the uptake coefficients shown here. So in order to kind of get this spike kind of midday, we would need to have a fairly large gamma, about 0.2. Something small like 0.002 just doesn't have the right profile at all. But even if we are able to kind of capture this spike, we're unable with any of these simulations to capture this initial morning increase, or really this slow decay to non-zero overnight. If we assume any sort of uptake coefficient, or the faster uptake coefficients, we should pretty much lose all of the imine overnight due to aerosol uptake. So one thing you could think was, I was only having the imine formed via OH oxidation. Maybe there's another way to form the imine. So we would expect that oxidation of methylamine by nitrate would also produce the imine, because the nitrate also proceeds via a hydrogen abstraction. But for the C1 amine, which is what I'm looking at here, or for the C1 amide, it's not fast enough. It's too slow to have any real consequence in the atmosphere. The next thing you might think is, well, maybe there's a source of C1 imine from other compounds, but given that the methylamine is the most prevalent one that we see, it's unlikely that any other source would be contributing. So one hint that we got here is this slower uptake coefficient here kind of has a similar sort of rate of decay at night as we see in the measured data. So what if instead we put some sort of morning emission that is correlated with that dew sort of emission of the methylamine, and then we let that evolve with that same lower uptake coefficient here. And you can see that we get a very nice match between the measurement and the model. So the one caveat here is you can see I'm just showing the normalized imine here because we weren't calibrated for the imine, and calibrating for the imine is a challenging analytical proposition, but one that we do hope to be able to do at some point. We don't really have good constraints on how much imine there was. These different scenarios obviously will give very different absolute concentrations, and thus having an absolute value would be useful for constraining them. But even so, I think this combined emission with aerosol uptake is probably the most likely scenario for this sort of molecule. And what is interesting about this is there's been no prior consideration of direct emissions of amines into the atmosphere. So what can an amine do in the atmosphere? So amines are interesting interesting molecules. They have a multitude of uses in synthetic and materials chemistry, mostly because of this kind of dynamic covalent chemistry is the term that's used frequently in the synthetic and the materials literature. And what that means here is that we can form and break this carbon-nitrogen bond by adding or subtracting water. So similar to aldol chemistry. So here we have the C1 imine. It can undergo hydrolysis to formaldehyde or ammonia. So one possibility for amine formation in dew would be something like this reverse reaction, where ammonia reacts with an aldehyde or a ketone. The water is evaporating, so we push it towards the amine. This is something we're looking into in lab. We can also have the amines react with other amines. We can grow chains that way. We can also have chemistry such as this. This might be familiar to some of you who followed some of the brown carbon literature, where this is the Mannich reaction. So we have an amine with two different ketones. Once again, it's a dehydrolysis. So this chemistry is interesting in that it could promote aerosol formation through some of this multi-phase chemistry beyond just the addition of the amine. Okay, and to conclude, I'm going to tell you a short story about urea. So what do we know about urea in the literature? It's been observed in aerosols and rainwater with large spatial variability. So less than 1 to more than 40% of water-soluble organic nitrogen. To our knowledge, this is the first ambient measurement of urea in the gas phase, though. There are reasons to think that it should be in the gas phase and that it might be increasing in abundance. So here I've shown fertilizer use in the US. On the left, it's the absolute, and on the right, it's fractional. Urea is shown in the red, and the nitrogen solutions, which also contain urea, is in the orange. And you can see that both the amount and the fraction of urea being used in fertilizer is rapidly increasing. So this is what our time series of urea in the atmosphere looks like. It is just shown in normalized counts per second. We're working towards a calibration of this molecule, and it's a little challenging. I'd be happy to talk about that more offline. And this is what we can see if we just take the average of the diurnal profile, which, as you can see here, there's kind of some greater variability than you might appreciate by just looking at this average here. But in general, what this sort of profile tells me is that it's probably not very reactive in the atmosphere. So we can look at some estimates of what we think it might do. It's not acidic or basic to any extent. The loss rate, the oxidation rates have not been measured, but using EpiSuite in the EPA, we can estimate OH oxidation rate constant of 2 × 10⁻12. So this means it'll be fairly long-lived in the gas phase. In the presence of urease, it undergoes very rapid hydrolysis. So that will generate CO2 and ammonia. So this is concerned for fertilizer application, and why many fertilizers actually include urease inhibitors. But if the enzyme's not present, this reaction doesn't, it's incredibly slow. It's C star, it's about 40 micrograms per meter cubed, so it'll exist primarily in the gas phase. And it has a very, very high Henry's law coefficient. And that provides it with a C star aqueous of 41 micrograms per meter cubed. So if we just take this diagram from Dammit et al. 2014, we can put that orange line on that value there, and we can see that at about 10 micrograms per meter cubed of water in the aerosol, about 20% of the urea should be in aerosol. At pH 4, since it's not very strongly basic, if we decrease the pH 1 to 1, it's only 22%. So I do expect that it would predominantly be removed via wet deposition. We do have some evidence that some of that variability could be due to dew. So once again, we have the dew point depression on the x-axis and then that maximum. So we do see a stronger increase in the morning on nights when there may have been dew. So we don't really know that much about the chemistry of urea and what it might do in the atmosphere. This is something we're starting to look at. But just like the amines, urea has numerous synthetic uses, most notably resin formation. So urea formaldehyde resins are one of the things that was the cause of the very high formaldehyde emissions in trailers that FEMA deployed post-Katrina. But there's also been more work, partly due to the formaldehyde issue, about making resins out of one of atmospheric chemistry's favorite molecules, glyoxyl. And so it is known that this sort of chemistry leading to this polymer growth occurs. It's unclear if it would actually occur under atmospheric conditions when you have different nucleophiles of varying strength, but is something that we're looking into. So there's the potential for some interesting chemistry that could lead to aerosol growth above just the direct partitioning of urea into the aqueous phase. Urea has also been of interest for new particle formation. So there's been a theory study showing that urea good at hydrogen bonding, so it can stabilize acids, although some lab studies indicated that it was probably not very effective in nucleating new particles. Interestingly, it has been observed in freshly nucleating clusters. So this is from the cloud measurements at CERN. And this is the composition of the ambiently charged ions in clusters. And the orange and kind of the light green are both clusters containing urea. So they did not add urea, it was a contaminant. But it is, if it's around, it does appear that it's participating in these clusters, even if it doesn't necessarily enhance the formation. Okay, so I started by motivating this a lot with new particle formation, and I haven't talked a whole lot about new particle formation. It's partly because during our campaign, we saw one new particle formation event. One does not give you, or at least during the part of the campaign that we have good measurements for, there was only one. Doesn't really allow you to say any conclusive insights. We can look at historical measurements of just the aerosol size distribution. So these are 3 years of measurements and just binned by the number of new new particle formation events based on their start time. And we do see that there is a fair number of events that start in the morning. And so there's maybe some hints that this evaporation of amines and ammonia could be an important source that leads to this. Because the other critical ingredient for the new particle formation would be the sulfuric acid, which was probably what's leading to more of these events in the middle of the day here. So there may be some hints, but what it really comes down to is we need more measurements. So to just wrap up with thinking really big picture, there's been a few different modeling works looking at how amines might contribute to new particle formation. So these are the results from one of those. On the left, we have the concentration. And then in the middle, we have the nucleation rate for just the amine-driven mechanism, and then the changes to CCN when amines were included. And in general, what this study found was that including amines resulted in a negligible change to CCN, mostly because the amines were pretty much only prevalent where there was already high aerosol. You can kind of see that from the distribution shown in panel A. So they concluded that for new particle formation below 500 meters, amines contributed to 6% of the events with uncertainties from 3 to 27. And so it may be important, it's probably not important aloft due to the short time period, the short lifetime of them. But what's also important to note is that we just don't have enough measurements of amine sources to really know if we're truly capturing the variability of these. So in this study, they assumed amines came from animals, oceans, and biofuel, and things like crops, fertilizers, fossil fuels, industry, and soils were all assumed to be 0. So what our measurements are showing is that the crops, fertilizers, and soils, at least, are probably not 0. There's also indications that there's amine emissions from combustion. So whether or not this will change anything, I don't really know. The amines are still going to be short-lived. However, what our measurements are showing is that there are things like urea, a molecule I didn't talk about today, pyridine, that are longer-lived and are being emitted. And so maybe they're important, maybe they're not. But we do need to understand them better if we really want to get a complete view of new particle formation. And so with that, I'll just leave you with some concluding thoughts about what we have learned from our ambient measurements. So we've learned that it's really complex sources and an opportunity for some interesting chemistry that at least I haven't thought about as an atmospheric chemist before, but that we know from the synthetic and materials literature that's kind of rich opportunities for polymerization. Organic nitrogen, it may be important for new particle formation, it may not, but what's clear is that we need to know more about the sources and the transformations of these compounds, because even if they're not important for new particle formation, they are playing an important role in the nitrogen cycle. And so we need to understand it from that point of view. And lastly, we really need more measurements of these compounds. I'm showing you here a week of measurements. We actually are funded to go back to Oklahoma. Well, we were supposed to go in May of this year, and that got canceled, but we'll be going in May of 2021, as well as in October of 2021, to look at this in more detail, different seasons, and that'll provide some insight, but we need to look at different environments as well. And so I'll just leave kind of these last points up here. They just kind of summarize some of the more details about what I went over, but I would love to take any questions at this time.
Thanks, Ellie. That was very interesting. Does anyone have any questions? If you have any, you have questions, please, you can unmute yourself and ask the question. I can start, I guess. So for the diurnal ammonia time series, the diurnal profile you showed, so you didn't mention sources of feedlot or cows, you know, like, are there any sources from feedlot?
Not in the immediate vicinity. It's mostly just fields, crops in the vicinity.
Okay. Do you also measure like methane or something like that?
No. So there's some measurements of methane, and we didn't see any correlations with that kind of morning enhancement of ammonia with either methane or CO at the site. And so doesn't really seem like the ammonia is being influenced by either animal husbandry or any sort of combustion process.
Okay.
There are also N2O measurements as well, but they don't really correlate with anything that we're seeing here.
Okay. Mary, do you have a question?
Yeah. So hi, Ellie. That was a nice talk. I was wondering, since you wrote down we need more measurements and you plan to go out again, if what you learned from the previous measurements, in particular, maybe identifying more with the emissions or quantitatively with the emissions, and especially with the dew, you know, can you get some more information about connecting those processes with your measurements?
Yes. So we're starting to do some synthetic dew measurements in lab right now to see, like, is this even possible with things that we know? If we know the starting composition for the dew, and if that looks like it is a reasonable sort of thing, we're going to try to maybe do some dew collection or something like that in the field to see if we can take that back to lab and analyze it. So I would like to go. I think looking at soil emissions are also an important way forward on this, but we're not set up to be doing that this coming year, unfortunately. So. But we will be calibrating for many more species this time around, and we have a much better inlet as well. So we're hoping those things improve the quality of our measurements.
Any more questions? If not,
I have a quick one.
Okay.
Is there, so with the resolution to separate the amine from the amide, you said that you needed a mass resolution of like 9,000. Is there any, could you use a Figaro to look at the aerosol component?
Yeah.
Or is there any plan to look at the aerosol component?
So you don't need 9,000 to get like the difference between the small amines and amides. The quadrupole just doesn't quite cut it. The 9,000 definitely becomes very helpful once we're starting to look at the higher molecular weight things. Yeah, which I didn't even talk about here. So we actually, we haven't specifically looked at amine chemistry with the Figaro, but Arub, who ran the instrument during the high scale data here, she did a collaboration with the University of Eastern Finland, where we did the Ethanol-CIMS with the Figaro, looking at ammonia and how it affects the composition of organic aerosol. And we saw a lot of imine type compounds and other things in the particle phase with that. So she'll be defending in December, and we'll be talking about that project then. So stay tuned.
Any more questions? If not, thank you again, Ellie. It was very interesting. And thanks everyone for joining. I think bye-bye, everyone. We will keep you posted with any future seminars. Thanks, Ellie.
Thank you.